welcome. In the last class we had completed whatever we wanted to cover in module 4. What we will do in this class is, since we have covered quite a few new concepts, let us look at them one more time, the concepts with some detail, not too much detail. This module 4 is on thermodynamics of solutions. Before we got into module 4, we looked at how a typical class is in terms of worthwhile achievements, the number in a class versus worthwhile achievements, and then I said I typically teach to people here, and the people here will need some help, probably they can discuss with me later. The people here are the ones who are expected to contribute a lot more to the area, the course, and so on and so forth. So for them, let me remind you once again, this everybody can do, please try it out. You do not really know where you are in this class till you evaluate yourself, the ease with which you can do this particular exercise. It is actually quite a tough exercise. This is called the choose, focus, analyze exercise. Students need to choose a problem of relevance to the bio industry or any human endeavor and analyze it using the thermodynamic principles taught in class. This is an open ended exercise which has been designed to improve the skills of choice, focus, and analysis in students. A concise report in the format that you think would best communicate your work is also deliberately done this way. Would be evaluated on the following criteria. The criteria are as follows: originality in approach would carry 15%, focus level 15%, depth of analysis 20%, quantum of work 20%, original contribution 20%, which means this should not exist earlier, that kind of a thing, and presentation, which is mainly communication. Communication carries 8%, and the professional appearance of the report carries 2%. So if you can do this over whatever time you want and you want to get back and discuss, that is also fine. Now we started looking at the thermodynamics of solutions. We said that in the previous module we had looked at pure substances, whereas many systems of biological interest consist of many substances. Sometimes we come across rarely a pure substance, but we need to understand the formulations for a pure substance well before we could appreciate that for solutions. That is the reason why we spend time on the pure substance first. Many systems of biological interest consist of many components, and when the components are mixed there could be changes in, for example, volume or enthalpy. What we said was, let us say that there are two components, each one has its own volume. Volume is easy to imagine, each one has its own volume. When we mix them together in a certain proportion, the final volume may not be the weighted average in terms of the mole fractions of the initial volumes. Okay, that is the nature of the substance itself, and that we have recognized here, and therefore we need to treat solutions differently. Therefore the thermodynamic properties, not just the volume, all the thermodynamic properties of the mixture or solution may not be the same as the weighted average of the relevant properties of its components, and if that indeed happens, it becomes an ideal solution. If the thermodynamic property of the solution is indeed equal to the weighted average of the components, then it is an ideal solution, otherwise it is a non-ideal solution. We will predominantly look at non-ideal solutions and ways to handle them. And we said we will look at some concepts for multi-component systems in this particular module, and we recalled what an ideal gas was in terms of chemical potential, equals mu naught plus RT ln P, and for a real gas the P gets replaced with a F. Mu equals mu naught plus RT ln F, fugacity, and F by P tends to 1 as P tends to 0. So this is for ideal gas and this is for real gas, pure component. And now what happens if we mix them together? And before that we said we will look at a concept of perfect gas mixtures and imperfect gas mixtures, which are essentially concepts which we will invoke at a later stage. It is just being presented here for completeness. It is nice to have all these formulations at one place. The perfect gas mixture is one for which the chemical potential of the component I for each component is expressed as mu equals mu I naught plus RT ln Pi, the partial pressure of the component I, and mu I naught is a function of temperature alone as earlier, and Pi is the partial pressure as we mentioned, and this is a perfect mixture of gases. For an imperfect mixture of gases, we said mu I equals mu I naught, which is still a function of temperature, plus RT ln Fi hat. Here Fi hat by Pi tends to 1 as the total pressure tends to 0. So these were the two hypothetical substances, perfect gas mixtures and imperfect gas mixtures, which are defined this way. And Fi hat by Pi was defined as the Fugassity coefficient Phi I, Fugassity coefficient of the component in the solution, as distinct from the Fugassity coefficient of a pure component, which was defined as F by total pressure P. And therefore, you could write for an imperfect gas mixture in terms of the Fugassity coefficient mu I equals mu I naught plus RT ln, you replace the Fi hat by Phi I Pi, and Pi is nothing but Pyi, the total pressure times the mole fraction. Therefore, mu equals mu I naught plus RT ln Phi I Pyi. Okay. This is all for perfect and imperfect, and what we would see more of in this particular module is an ideal gas solution. We had an ideal gas and non-ideal gas. Now we are looking at an ideal gas solution and a non-ideal gas solution, and we said with this formulation it is easy to extend them to either liquid or solid solutions also, mixtures also. So ideal gas solution is one for which the following relationship holds for every single component: mu I equals a certain mu I hash plus RT ln Yi. Yi is the mole fraction of the component in the ideal gas solution. Mu I hash is a function of both the temperature and pressure, but not necessarily equal to mu I naught plus RT ln P, and the ideal solution of liquids and solids can also be expressed in the same way: mu I equals mu I hash plus RT ln Xi, where Xi is the mole fraction of the component I in the ideal solution of a liquid or a solid. The equivalent expressions in terms of the Fugassity coefficients were also given. Now the non-ideality is brought about either by a Fugassity coefficient for a gas mixture or an activity coefficient for a liquid or a solid mixture solution. So for a non-ideal gas solution, mu I equals mu I hash plus RT ln Phi I Yi, and the equivalent is given. For a non-ideal liquid or solid solution, it was mu I equals mu I hash plus RT ln gamma I Xi, with gamma I tending to 1 as the mole fraction of the component I tends to 1. This of course was expressed in terms of Fugassity and so on for equivalent expressions. Gamma I is the activity coefficient, and note that gamma I is a function of temperature, pressure and composition, whereas mu I hash was only a function of temperature and pressure. And we said that definition so far for a non-ideal liquid or a solid solution works well for many solutions. let's concentrate on liquid solutions, works well for many liquid solutions, but it does not work so well when one of the components is either a gas or a solid at the temperature and pressure of interest of the solution. For example, it has many biological solutions have, or many solutions of biological interest are of that category. For example, the solution of glucose, if glucose is in water, let us say, then it is going to be a liquid at a certain mole fraction of glucose, but if you increase the mole fraction of glucose to 1, it is going to be pure glucose, which is going to be a solid at the temperature and pressure of the solution. Therefore, that formulation will not work, and a similar example was that of oxygen. Oxygen in water is a liquid at the temperature and pressure of interest for growing cells, whereas oxygen itself is a solid, itself is a gas. So if you increase the mole fraction of oxygen in the solution to 1, then the phase changes, it becomes a gas phase at the let us say at higher mole fractions, definitely at a mole fraction of 1, and therefore we need to have a different formulation to be able to handle that. The same formulation that we presented will not be able to handle that, and we did that by noticing that at the extremes, that is when the mole fraction either tends to 0 or 1, the behavior is ideal. We had used that fact, and then we had come up with a separate expression for the solvent and a separate expression for the solute. Both need to be used together in the model for chemical potential. The solvent is indicated by the subscript O and the solute is indicated by the subscript I. For example, mu O equals mu O hash plus RT ln gamma O XO, and gamma O tends to 1 as XO tends to 1 for the solvent, and for the solute mu I equals mu I hash plus RT ln gamma I Xi, and gamma I tends to 1 as Xi tends to 0 here. This is for the solute, and both these put together as equation 4.9. So these are the various models for the chemical potential for the various kinds of solutions that we have seen, from the ideal to the real, and we did make a difference between the gas and liquid and solid. Now, by considering the ideal solution and manipulating the expression mu I equals mu I naught plus RT ln Fi hat, we came up with an expression, and this argument was important there. We came up with this expression mu I hash minus mu I naught equals RT ln Fi hat by Yi. We said that the left hand side is independent of composition, therefore the right hand side should also be independent of composition, but you have a term for the composition Yi here. Therefore, the only way by which the right hand side will be independent of composition is if the ratio Fi hat by Yi remains a constant when Yi is changed, and we had used that argument to get to this expression Fi hat by Yi must be equal to Fi by 1. Fi hat is the fugacity of the component in the solution, and Fi is the fugacity of the pure component when Yi equals 1, and therefore in such a case Fi hat can be written as Yi times Fi, which became powerful because we could get an estimate of Fi hat, some sort of a hypothetical quantity, well I should not say a hypothetical quantity, but not so easy to determine quantity, as a function of Yi and the fugacity of the pure component. Therefore, there was a way of estimating Fi hat by this expression, and this was actually called the Lewis and Randall rule. This of course is valid only for an ideal solution. In an ideal gas solution, the fugacity of each component is equal to the mole fraction times the fugacity, which it would exhibit as a pure gas at the same temperature and total pressure. and this we have already seen. Then we went into something called partial molar properties, which would give us a way of handling our initial problem. We said that in terms of volumes, we started in terms of volumes, the volume of the final solution may not be equal to the weighted average of the volumes of the components, and if we need a formulation to express it that way, that would be in terms of partial molar properties. And we had defined the partial molar property for any property as MIT hash equals dou ni of MT at constant Tp and all other n's remaining a constant. This you could write for any of the extensive properties Ut, St, Ht, At, Gt or Vt. And of course, it was quite obvious that the partial molar property may not be the same as the pure state property at the same temperature and total pressure, and the total property, extensive property, can be computed from the partial molar properties as the sum over Ni, the mole numbers, times the partial molar property of that component. You sum them over all the components, then you get the total property. To be able to express it this way was the need to define a partial molar property at all. And then we wrote the complete set of partial molar getting the of the expressions for getting the total properties in terms of the partial molar properties. This is total volume, total internal energy, total entropy, total enthalpy, total Helmholtz free energy and total Gibbs free energy. All this in terms of the partial molar properties was written down. And then we went into arguments of with using the expansion of the total derivative dmt, and dmt dou mt dou ni at constant Tp Nj is nothing but the partial molar property here. Therefore, you get this in terms of temperature, pressure and the number of moles variation. And we got this particular expression, which is a useful expression to have, sum over Ni dmit hash equals 0. And if you divide this expression, equation 417, by the total number of moles, we got sum over xi dmit hash equals 0. This is a very useful expression to have. This is equation 418. And then we looked at how to estimate the partial molar properties from experimental data. The experiments that we are interested in are called mixing experiments, where the initial values are measured and the total value upon mixing is measured. For example, if we take volume, since it is easy to imagine, if V1 and V2 are the molar volumes of the pure components 1 and 2, and V1 T hash and V2 T hash are the partial molar volumes in a solution containing N1 moles of component 1 and N2 moles of component 2, then the difference in volume upon mixing, which is what actually is measured and plotted, is N1 V1 T hash plus N2 V2 T hash. This is the volume of the solution after, and this is the volume before, that is the volume of the pure components N1 V1 pure, the volume of the pure component 1, N2 V2 the volume of the pure component 2. Note these are molar quantities, therefore, when you multiply it by the mole numbers, you get the total quantity. So, after mixing volume minus volume before mixing, that is delta Vt, which can be transposed into a convenient form to get 1 minus x2 times V1 T hash minus V1 plus x2 times V2 T hash minus V2, and this is what is plotted. Delta V, the volume change upon mixing as a function of the mole fraction x2, if it is plotted, we get a curve something like A G B here, and if we are interested in the partial molar volumes at the point E, we said we draw a tangent to the curve at the point E, and we actually proved this, that the intercept of the tangent on this axis when x2 equals 0 or the distance AC gives the partial molar volume 1 V1 T hash, and the intercept of the tangent on the line on the ordinate of x2 being equal to 1 or the distance dB gives us the partial molar volume of the second component V2 T hash. And this is we had gone through expressing equation 420 in terms of the derivative and so on, and we had formulated it in such a way that some of the quantities that we are interested in would correspond to distances on the delta V versus x2 diagram, and therefore we went about proving that indeed, or deriving that you can indeed use the distances on the delta V versus x2 graph to find out V1 T hash and V2 T hash. Actually what you are finding out is V1 T hash minus V1, that is the intercept, not the V1 T hash itself. I should correct myself here, you know, this distance AC is actually V1 T hash minus V1 and this distance is V2 T hash minus V2, and since we know the molar volumes of the pure components, V1 T hash can be computed from this distance and V2 T hash can be computed from this distance. Please make that correction. This is the way we went about deriving that particular expression. Please look through the derivation one more time. If you have any difficulties, we can always discuss. This is the way we showed, you know, there was some equality of distances. AE is the same as CF, and therefore we could cancel the 2, and therefore V1 T hash minus V1 at the point E became GE minus F minus GF, right, GE minus GF, and which is FE. FE is nothing but CA, which is the intercept of the tangent on the x2 equals 0 line. Then we worked out an example by which we could find out the partial molar volumes for a case of relevant interest. And then we started looking at the relationship between excess properties and activity coefficient, and we first saw what an excess property was. Excess property is nothing but the difference between the actual property and the ideal property, and we said excess properties are defined the same way and play pretty much the same role as the residual properties for pure components. Residual properties we had seen in module 3, you can go back and refer to that also. In other words, MR, the residual property, is defined as M, the actual property, minus M ideal gas. An excess property of a solution is the amount by which its relevant thermodynamic property exceeds that of the hypothetical ideal solution of the same composition, and we had given this MTE equals M minus MT ideal gas. And then we started looking at one of the excess properties, which is the excess Gibbs free energy, we had a very specific objective in mind, which was to develop an estimate for the activity coefficient using the excess Gibbs free energy. Then we said the total Gibbs free energy was sum over Ni times mu I, and then we went through the difference between the total and the ideal, that gives us the excess, which will turn out to be only this term on the right hand side, RT sum over Ni ln gamma I, and therefore dGTE, the derivative, the total differential of GTE dGTE by chain rule would turn out to be RT times summation over Ni d ln gamma I plus summation over ln gamma I dNi. Then we went through an interesting derivation or an interesting proof, where we started from a very fundamental Gibbs-Duhem equation, and pretty much without any assumptions, we actually showed that for any case sum over Ni d ln gamma I goes to 0. Okay, we had worked that out together, so that it will strengthen some of the ideas in you, and therefore we were left with dGTE equals RT times sum over ln gamma I dNi. This is the process that we went to, very interesting kind of a derivation, you may want to look at it again. It also shows the level of care or carefulness that one needs to exhibit while doing these kind of manipulations. And this is where we brought these two terms in terms of, we had used the reciprocity relationships to convert the third and the fourth terms as equivalent to the first and the second terms with opposite signs, and therefore we could get rid of them, and we were left with just this, which is sum over Ni times internal sum over all k dou mu I dou xk at constant Tp xj dxk equals 0, and what would be easier if we divided throughout by sum over Ni, then this Ni by sum over Ni would become xi, here it goes to 0 anyway, therefore it became xi sum over xi times internal sum over k dou mu I dou xk Tp xj dxk equals 0, and from here we had used the expression for mu I as mu I hash plus RT ln gamma I xi, and by an interesting formulation, beautiful actually the way it turns out, these are just writing out all the terms, we need to write all the terms if we need to do it properly, but for ease we took one term at a time, and also we had noticed or noted that mu I hash is a function of temperature and pressure alone, and this became handy when we had taken the derivative with respect to composition, and such terms would vanish because this is not a function of composition, whereas gamma I is a function of temperature, pressure and composition, therefore all terms would remain there. And after going through some more algebra, which we went through together, we got for the first term alone x1 times d ln x1 plus d ln gamma 1, and if we considered all the terms and combine them appropriately, we got x1 d ln x1 plus x2 d ln x2 plus so on xp d ln xp, p is, remember, is the total number of components, plus x1 d ln gamma 1 plus x2 d ln gamma 2, and so on till xp d ln gamma p equals 0, and which can be written as sum over xi d ln xi plus xi d ln gamma I equals 0, and xi d ln xi is nothing but each one of these terms is nothing but xi times 1 by xi dxi, d ln gamma I is 1 by xi dxi, therefore, we could cancel xi to get dxi, and then the sum over all dxi's would be d of the sum over all xi's, which would be d of a constant, excuse me, d of a constant, which is nothing but 0. Therefore, we obtained xi d ln gamma I equals sum over ni d ln gamma I, it is just multiplying by the total number of moles, which is 0. This was our equation 430, and from here we could, when we went back to the expression for dGe, we had those two terms, we had gotten rid of one term, and therefore, only one term remains here, dGe dGte by RT equals sum over ln gamma I dni. This is what we are left with in a nice way, but what this also tells us is, if you take the derivative, the partial derivative with respect to a certain ni with temperature, pressure and all other n's remaining constant, then that would actually give us ln gamma I. We had used this as the basis to come up with models, or at least to see the models for obtaining activity coefficients if GTE by RT is known as a function of composition. Earlier we saw some intuitive models, rather before that I should say we started looking only at binary systems, the activity coefficients in binary systems from then onwards, and earlier we saw some intuitive models by Margulet, which gave us GE by RT equals A21 x1 plus A12 x2 times x1 x2, and by following the differentiation with respect to one of the mole numbers and suitable recombination, we could convert it this way, or we could do it in terms of x1 x2 also, that is what we did later, but here we did convert it to n1 and so on. We got expressions for gamma 1 and gamma 2. For example, in the case of Margulet, we got ln gamma 1 equals x2 squared into A12 plus 2 times A21 minus A12 times x1, and ln gamma 2 was x1 squared times A21 plus 2 times A12 minus A21 times x2. And then we looked at what happens at infinite dilution, ln gamma 1 infinity, just by substituting this into the model we got that ln gamma 1 infinity was A12 and ln gamma 2 infinity was A21. We also saw the other models, the Redlich-Kistler model, which is a very simple GE by RT equals B x1 x2, and we got expressions for ln gamma 1, ln gamma 2, ln gamma 1 was B x2 squared, ln gamma 2 was B x1 squared, and also the expressions at infinite dilutions. Van Laar model, which is one of the popular models, G by RT equals A12 dash A21 dash A12 dash x1 plus A21 dash x2, this A12 dashes A12 dash and A21 dash are constants for a given system, and from that we got the expressions for ln gamma 1 as A12 dash times 1 by the square of 1 plus A12 dash x1 plus A21 dash x2, and ln gamma 2 was A21 dash times 1 by the square of 1 plus A21 dash x2 divided by A12 dash x1. And we also saw the infinite dilution expressions, and then we started considering the Wilson model. Apart from the others which had some sort of an intuitive basis, the Wilson model was based on a theoretical concept, a local composition concept. The local composition concept, just for information, we are not going to look closer at this in this particular course, it is outside the scope of the course. The local composition is postulated to account for the short range order and non-random molecular orientations that result from differences in molecular size and the intermolecular forces. We get into statistical thermodynamics, you would need to worry about all these things, and therefore this Wilson model has a better grounding in the molecular theory of solutions, and so are many other models such as NRTL, UniQuack, UniFac, and so on and so forth, that are available in the literature. They were developed ages ago, decades ago, but which are very useful for finding out activity coefficients, for estimating activity coefficients from the data, from the models. Wilson model was GE by RT equals minus x1 ln of x1 plus x2 times gamma 1 2 minus x2 ln of x2 plus x1 times gamma 2 1, and gamma 1 2 and gamma 2 1 are the Wilson constants for a particular system, and similar procedures as for the other models would yield. This was again left to you as an exercise. Hopefully you did them. If not, please do them and convince yourself that this is indeed the case. Ln gamma 1 equals minus ln of x1 plus x2 gamma 1 2 plus x2 times gamma 1 2 divided by x1 plus x2 times gamma 1 2 minus gamma 2 1 divided by x2 plus x1 times gamma 2 1, and ln of gamma 2 equals minus ln of x2 plus x1 times gamma 2 1 minus of x1 times gamma 1 2 divided by x1 plus x2 times gamma 2 1 2 minus gamma 2 1 divided by x2 plus x1 times gamma 2 1. So, this is actually the same in both these expressions, the second combination term, and we saw the expression for infinite dilutions also. And then we worked out an example. This example was deliberately chosen to tell you something more. The first one is a direct calculation. This is the example was with respect to isopropanol. Isopropanol has many biological applications. To design the distillation process for purifying isopropanol, the activity coefficients are required, and compute and compare the activity coefficients for an isopropanol water system with mole fraction of isopropanol being 30%, using the following data taken from the literature. The Van Laar constants and the Wilson constants for a particular condition were taken from the literature, and we went through the calculations. You went through it first and then I showed it to you. We found that in the Van Laar model we got gamma 1 was 1.331 and gamma 2 was 1.119, whereas in the Wilson model, using the Wilson model, we got a gamma 1 of 1.965 and gamma 2 of 1.276. Of course, different models would give different gamma values, and what is better, to get better and better estimates, different models were developed, or better and better models were developed, and some of the model names we saw in the earlier part of this particular subsection itself. And this is what we did in terms of thermodynamics for solutions, or of solutions, in this particular module. When we begin the next module, there are two more modules that we will look at in this particular course. The first module, or the fifth module in the sequence, is on phase equilibria, and the sixth module is on reaction equilibria. We will use whatever we have developed so far. Just to give you a flavor, after a review we looked at thermodynamic properties, we defined thermodynamic properties and presented ways of manipulating them, getting useful information from whatever is available easily, and so on and so forth. And then we also found that there were ways of expressing the not so easy to measure thermodynamic variables in terms of easy to measure thermodynamic variables PV and T. And then we looked at the thermodynamic aspects of pure substances and thermodynamic aspects of solutions, and then we are going to use all of those in predicting phase equilibria and coming up with relevant useful predictions for reaction equilibria also. That is what will follow. See you in the next class.